Anyway, thank you for being here. Dick Iverson is a USGS scientist emeritus. He's a longtime watershed resident, watershed group participant and resident. He received his PhD from Stanford University with an emphasis on geology, hydrology, and geophysics. He became a research scientist at the USGS Cascades Volcano Observatory in Vancouver, Washington, where his work focused mostly on the dynamics and hazards of debris flows. So I asked Dick to kind of stretch a bit and give us a little bit of context on climate modeling to sort of help kick off this series on climate in the watershed. So this tonight is focusing on the glaciers. Next up, we'll have Anders Carlson, who I'll introduce after Dick gives his presentation. And then we'll move in the next month in April to mitigation and adaptations, sort of the focus on things that we can do or that the watershed group is doing that address climate change from a mitigation and adaptation perspective. So, Dick, thank you very much.
Dick, I'm sorry, my face is there.
It's okay. If anything goes catastrophically wrong, you'll get blamed. So as Cindy mentioned, I'm not a climatologist by training, but I do have a pretty strong background in a lot of related sciences, and I'm very interested in climate change. And so really, I'm just going to give you a very brief summary about kind of the status of knowledge right now about how Earth's climate is changing globally, and also a little bit about how it's changing locally here in the Hood River Valley. Let's see here. So this first slide, I want to make a couple points in passing about the context for this slide. And that is that I took a number of graphics from a group called Berkeley Earth. And Berkeley Earth is a group of scientists who are based in Berkeley, California, but they have backgrounds that stem from UC Berkeley, most of them anyway, but they're not officially part of the university. So it's an independent group that gets most of its funding through charitable contributions. And they're one of several groups worldwide that has been assembling data sets on Earth's warming climate, and they happen to put out some pretty nice graphics. And so I've exploited that for these first set of graphics in this talk. So this simply shows the global average temperature on Earth, and it's in degrees Celsius. Keep in mind that degrees Celsius is loosely speaking about 2 degrees Fahrenheit. Most of us are more familiar with Fahrenheit. More precisely, it's 1.8 times, but it's useful to just think of it as 2 times. So what this is showing is deviations in temperature, or what they're calling the temperature anomaly, relative to a baseline up through the time 1900. And what it shows is that since that time, worldwide, the temperature has warmed on average about 1.5 degrees Celsius. So that's about 3 degrees Fahrenheit. The jagged line that you see there is the actual annual data that they've compiled worldwide from literally thousands of data stations. You can probably see, if you're sitting close enough anyway, the little bars on some of those data. Those are 95% confidence intervals. And if you look, you'll see that those confidence intervals become much tighter as you go on in time. That's, of course, because the confidence in the old data is not nearly as good as the confidence in the new data. But nonetheless, it's data just the same. The confidence intervals help you understand what the uncertainty range is. The red line is just a smooth version of the data. I think it's probably what they call a spline function, although I'm not certain about that. So looking in a little more detail, you can segregate Earth's temperature into the land surface temperature and the ocean temperature. And so this now shows the land average temperature, and you can see that its anomaly relative to that early reference period is about 2 degrees Celsius, so about 4 degrees Fahrenheit. So that's really quite a bit of warming. If you look instead, at the ocean average temperature, you can see that that's only about half as much, about 1 degree Celsius. That's unsurprising because water, of course, has a very, very high specific heat, meaning that it can absorb a great deal of heat without changing its temperature very much. And that's why we see greater warming on the land than we see in the oceans. This now shows global warming by month, and you'll notice that those uppermost lines are for the most recent years, 2022, 2023, and 2024. Those you can see are well above the curves for the data trends for the preceding times for almost every month, but especially in the summertime, in what we call the summertime here in the global north, meaning July, August, September. It's also the case, and this actually shows up on, I'll go back to this earlier slide, the global average temperature. It's worth noting that the 10 warmest years in history have been the 10 last years on Earth. So that's pretty compelling. If you think the 10 warmest years of all time have been just the last 10 years, that's a pretty conspicuous pattern. So I thought I should show this illustration simply because it shows the same global warming trends as compiled by different research groups, 5 different groups in this case. So one of them is the Berkeley Earth group, but there's also the UK Hadley Meteorological Office, the NASA Earth Surface Temperature Compilation, US Oceanographic and Atmospheric Administration, what we commonly refer to as NOAA, and the European Weather Forecast Center. And you can see there are some differences because these different groups are using slightly different data sets. But nonetheless, the patterns are extremely well established, regardless of which group is compiling and analyzing the data. And so it's extremely compelling, in my opinion. So the only illustration I'm going to show that relates to modeling is this one. And this shows a comparison between the temperature anomaly trends that I showed you earlier, the black squiggly line there, versus what comes out of a relatively simple numerical model of Earth's climate, which is developed by the European Geophysical Union. And it's called the Finite Amplitude Impulse Response Model. I'm not going to go into detail as to what that exactly means, other than that it's not as elaborate as some other climate models. What it helps show, however, is that looking for sources of what is it that's actually causing this warming climate, a large percentage of it can be attributed to CO2 emissions or increasing concentrations of carbon dioxide in the atmosphere. An additional component is related to methane accumulation in the atmosphere, and then other greenhouse gases. That's the other GHC there. And other greenhouse gases include relatively innocuous things like water vapor. Also includes chlorofluorocarbons, which are noteworthy because, of course, those are the things that have threatened Earth's ozone layer. And there are other more sort of exotic things like nitrous oxide, which is also a greenhouse gas. But the bottom line here is that the model trends more or less match the observational data. However, they're actually getting outpaced by the observations. Earth's climate is warming faster than most models predict. Now, that's probably due to feedbacks that aren't incorporated in every model, and especially in this relatively simple model. An example of a feedback that's really important, for example, would be warming of the Arctic and subarctic permafrost, which causes it to melt, and that releases a lot of methane in the process of melting, and that methane is a very, very potent greenhouse gas. So, so again, in my view, the picture is pretty compelling. Now I want to turn more towards what's going on locally here, and if you look at this illustration of Earth, and focus in on the Pacific Northwest, it's maybe a little hard to see, but if you can probably pick out Puget Sound, which is a little black thing sticking down along the west coast of North America there. And you can see that we live in an area that has not warmed. Well, this is just for 1 year, for 2024, but it's a good year to choose because that's the warmest year on record thus far. what it shows is that there's a tendency for our particular part of the Earth to not be warming as quickly as some other places. And that's particularly true compared to the high latitude places, the Arctic and subarctic, where the warming has been at a much greater pace than it has been down here. So with that as a lead-in, I'm going to turn to some local data that I've compiled. And I took these data from a website that has been developed by the PRISM group at Oregon State University. PRISM is an acronym. I need to pull out my cheat sheet here to remember what it stands for. It stands for Parameter Elevation Relationships on Independent Slopes Model. And what it is basically a very sophisticated data interpolation scheme that allows you to kind of pick a point, and I should say not really a point, but on a grid that's 800 meters on a side that spans the surface of the United States. You can pick out an individual cell on that grid. And so I've picked out a cell that's sort of in the middle of the Hood River Valley, specifically right around Odell, so at an elevation of about 600 feet. And I've pulled up the data interpolated from various data recording stations for that particular location. And the interpolation is really pretty sophisticated. It involves all the following. Location, elevation, proximity to the coast, topographic aspect, meaning the direction the topography faces, topographic position, and the orographic influence of terrain. And so it takes all those factors into account to provide data for any particular spot that you choose. And so you could query these data, for example, for the summit of Mount Hood if you wanted to. Those probably wouldn't be very good because there aren't many weather stations near the summit of Mount Hood, but nonetheless, this is for the kind of the center of the Hood River Valley. And what it shows is that if you look at the blue line there, that's the average temperature for the period 1895 to 1980. And it shows that it's right around 50 degrees Fahrenheit. I've switched scales here. I'm now looking at Fahrenheit degrees rather than Celsius. But you can see that since 1980, there's been a climb. And that's probably best illustrated by the red line, the smooth red line, which is just a five-year moving average that I've calculated from these data. And what it shows is that up to the present, although actually this is only through 2023, because when I pulled these data up, they hadn't yet been updated for 2024. But as of 2023, you can see that the warming here locally has only been about 1.5 degrees Fahrenheit. So that's only about half of that local land average for the entire planet. And I think there are likely a few reasons for that that are pretty easy to identify. And a lot of it just has to do with our particular unique geographic setting here. We get a lot of flow of cool air through the Columbia River Gorge in the summertime, air that's basically being pushed in from the coast where the air is denser and heavier out there. And so we get those persistent cooling west winds in the summertime here. Conversely, in the wintertime, we oftentimes get an easterly flow, not as strong as the summer westerlies, but that easterly flow is bringing in cool air from the high desert, basically, in eastern Oregon and Washington. And then in addition to that, we get cool air that tends to move down valley from Mount Hood. The cool air is denser than warm air, and so it tends to just flow downhill. And you can really feel that sometimes when you go up the valley during the summertime. You can feel that cool air just coming down from the mountain. And so we've been very fortunate thus far here in that our warming locally has only been about half of the global average. So that's a good thing, but there's no guarantee that it's going to last as the climate continues to change. And then I'll show one last illustration here. I also pulled up the precipitation data from the PRISM data collection. And this shows the long-term average, 1895 to 2023. And you can see it's right around 30 inches a year of precipitation here, which is no surprise. But you can see that recently, particularly following the really wet year that we had in 1996. And those of you who lived around here in 1996 probably recall that winter because it was devastating around here. Almost every river flooded. There were landslides and debris flows all over the place. There's a great deal of damage done, a lot of lives lost and so forth. So 1996 was a very anomalous year, but you can see that since that time, on average, the data fall below the mean. So there's some indication that it's actually getting drier here as well as warmer. And that's, you know, also a cause for concern, although this trend isn't, you know, it's not terribly well established at this time. So that's really all I have to present. Now, is there time to take a few questions?
Yeah.
You mentioned that local warming is half the global average. Can we expect the local warming to continue to be more moderate, or is there a possibility that the local warming will catch up to the global average? So,
Yeah, I doubt, at least not in our lifetimes, I doubt that it's going to actually catch up with the global average. Simply because of our unique setting here. Again, having the influence of the cool air coming in off the coast and also coming down from Mount Hood. And also the fact that that global average is partly influenced by the extreme amount of warming that's going on in the Arctic and subarctic, you know, where it's there that the temperatures have warmed by something like 6 or 7 degrees. And that's what's causing the melting of the permafrost and the, you know, the disappearance of the polar ice pack and so forth. You know, it's a pretty extreme situation. And as the climatologists like to say, what happens in the Arctic doesn't stay in the Arctic. Okay. In the temperature, yeah, I'm not sure what that was all about, to tell you the truth. I wasn't living in the gorge at that time. Maybe somebody who was living here would have, maybe it was a particularly cloudy in summer or something. I don't know. Had to cut her off.
Yeah, but we could, if they'll, I think there'll be time after Anders is done, we can have more questions. Thank you, Dick.
Sure.
Right, Anders, all you.
Hey.
Okay, and I'm
Oh,
gonna introduce Anders.
Share, man.
Yep.
Gotta give me sharing abilities.
Okay, Anders Carlson is about to give his presentation, but I wanted to let you guys know a little bit about Anders. He's speaking to us out of Corvallis, which is okay. I wasn't interpreting your sign language. Okay, so Anders is fell in love with glaciers as an undergraduate student while conducting research at Matanuska Glacier in Alaska. And one just small world thing I need to interject with is that Anders told me that at some point, maybe during his graduate work, you said, Anders, that he worked with Dick's brother in like Norway. Would it have been Norway? Yeah, I'm sure Anders will correct me in a second. But anyway, just very small one. So anyway, after receiving his BA in geology and German from Augustana College, Illinois, he earned an MS at the University of Wisconsin-Madison and a PhD at Oregon State University in glacial geology. Following a postdoc at Woods Hole Oceanographic Institution, he was a professor at the University of Wisconsin-Madison and then Oregon State University before founding the Oregon Glaciers Institute. As a post-academic day job, he is the senior climate scientist at the Oregon Climate Law Firm out at Eldridge Trust. Anders has studied glacier climate change for over 25 years in the United States, Canada, Greenland, Svalbard, Scandinavia, Patagonia, and Antarctica. I think that's a pretty enviable list of places that you've studied glaciers, Anders. So thank you for joining us over Zoom. I think this is a nice thing to try out. And just so you know, Jonathan, any idea guess at how many people we have in the room?
58.
58. We have like 58.
Very accurate guess.
Let me record it. Everybody smile.
Yeah.
That's
Yeah.
great.
So thanks again. And then there'll be time for questions at the end. And I think you probably won't be able to hear everybody in the audience on there, so we'll kind of do we've got a microphone here, so we'll figure it out. Anyway, thank you very much.
Great. I'm glad this worked out in the end. I could come over virtually to Hood River. I wish I was there in person. I love the town, and it just wasn't in the cards to getting up there and getting back to Corvallis. So I will give kind of an overview of what the glaciers on Mount Hood have been doing in this century, and then compare it to the last century and focus in then as well on the Hood River Watershed. And just to give a brief summary about what the Oregon Glaciers Institute is, we were founded in May of 2020, and we're a volunteer nonprofit that focuses on tracking Oregon's glacier change and how they're responding to climate change, and relaying that then to communities, interested communities, and policymakers, like what I'm doing right here. So we're coming up on our 5-year anniversary, and so yeah, if you want to learn more about us, check out our website. There's a link down at the bottom, or you can just look up Oregon Glaciers Institute and you'll pop up on Google. So just kind of an overview of Mount Hood and its glaciers. On the right here, I'm showing you, this is a figure taken from the Hood River Watershed Group's website, showing you the Hood River Watershed, and then it's summed up here in Mount Hood. And in the 1980s, Mount Hood still had 12 named flowing glaciers. And by the late 1980s, the one Palmer really was a glacier as of 1981. It ceased to be a flowing glacier. It thinned down. The ice was no longer deforming and became the Palmer snowfield that we know these days. As of 2000, 6 of the 11 remaining glaciers on Mount Hood were in the Hood River Watershed here. Another 3 glaciers were in the Sandy River Watershed on the western to the southwestern side. And then the White River Glacier here is the only one that's in the lower Deschutes watershed. It wraps around and comes, it's what meltwater goes into the Columbia River around the Dalles. And then lastly, there's one glacier, Coleman Glacier, up at the summit that straddles the Sandy River and the lower Deschutes River watersheds there. One of the things that initially started our work was the fact that on any U.S. Federal map, whether it be from the U.S. Geological Survey or the Forest Service, the outlines of the glaciers and ice bodies in the Oregon Cascades from the 1950s. So they've never been updated on federal maps since first made post World War II. That said, the last time anybody did any field mapping of a glacier extent on Mount Hood was in 2004. And then there was an updated remote sensing extents published from satellite imagery in 2015-16. So there are some information here going up to present since the 1950s. The 2015-16 information, though, had no field checking, and that becomes problematic in Oregon's glaciers because there's a lot of rockfall, and you may be standing on ice, or you could just be standing on the volcano without any ice underneath you, and you can't really tell unless you actually out there being able to check to see if it really is ice under the rock. So what we did, kind of a serendipitous thing occurred. A mountaineer, medical doctor, Steve Boyer, who is a Mazama member, actually had gotten his master's degree in the late 60s in geology with his master's advisor was the PhD advisor, my PhD advisor, John Andrews at University of Colorado. Then Steve went on to then become a medical doctor, and he was like at Mount Everest Base Camp as a doctor. But he, in 2003, went out and took an early GPS and an early digital camera and documented the extent of glaciers on Mount Hood. Posterity then. And we were able then 20 years later to go back and recreate his study to see how these glaciers changed, combining that also with extensive mapping over multiple years going out to this area, and then also using updated satellite imagery from 2023. So updating 2015, 2016 glacier outlines. So this is a figure here, map here. This is the most recent U.S. Forest Service map out there from 2016. The glacier outlines on here, though, are the same extents that were put on the 1950s U.S. Geological Survey maps. And so this is what you still get when you buy a map to go hiking on Mount Hood. The snow and ice bodies are what they were during the Eisenhower administration. And the black dots here are showing you locations where Steve went out and measured ice extent and took some photos. And there's other locations he had further distance from photos. So we were able to recreate his study. And I'll just show you right now the glacier change for the glaciers not in the Hood River Watershed. And the first one here is looking at the south side of Mount Hood. This is over at Ski Bowl, looking across. Here's in 2003 on the left and 2023 on the right. At Zigzag Glacier, here's the Palmer Snowfield. You can see White River Glacier over here just sticking up, and then Coleman up in the summit here. And Zigzag Glacier is dramatically retreated in the last 20 years. It's still a flowing ice, but it doesn't have any snow left on it at the end of the summers. And so it's probably going to stagnate soon and then go away, kind of like what's happened to Palmer Snowfield. Palmer would not even be an annual snowfield if it wasn't for Timberline Lodge farming snow and building it up at high elevation so they can still have their summer snow camps. And then you can see Coleman Glacier at the top part there has retreated as well, losing a lot of its area too. Here's Sandy Glacier on the northwest side here, and 2003, 2023. The key thing here is that it's famous for its ice caves, and you can see how they have retreated up the slope. And the other thing is this area over here has all been, ice is completely melted from that region there. And there's been a lot more debris cover building up on the glacier. And lastly, Reed here, it was terminating on ice cliffs, so it couldn't really extend much further down valley unless it got a lot colder or it snowed a lot more. So it's was already constrained. So it hasn't retreated, its aerial extent hasn't changed as much, but it's definitely thinned down between these two over the 20 years between 2003 and 2023. So just to summarize up the larger changes on Mount Hood before delving into the Hood River Watershed, the left here map shows in white the extent of the glaciers in 2023 or remaining or remnants of glaciers in case like Palmer. Blue is in the 2015 and 2016 extent. Purple is areas in 2004, the last time they were field mapped, and this is only available for 7 of these glaciers, not all 12. And then yellow is their early 1900s extent. So we're able to then take these to then build a time series of how fast the glaciers have changed in Mount Hood since the early 1900s, and compare that then against changes in precipitation and temperature, which I'm showing over here. Now, these are different. The records I'm showing here are regional changes. So these are the changes in temperature and precipitation for the whole Hood River County, which contains much of Mount Hood. So it's a regional record. Rather, what Dick was showing there was a point location. And so this gets the, as you narrow down closer and closer to smaller and smaller levels, the temperature gets, crazier. Like just think about if you're under a tree on a sunny day, you go under the tree, it cools down a bit because you're out of the sun, and you go out of the shade, it gets a lot hotter. So the more granular it get, the noisier the records get. And so we are comparing it here to the regional temperature change, which is why it looks different from what he was showing from the Prism group. And these are what NOAA produces. So here's the summary then. Since 2000, again, using these records, the glaciers on Hood have lost 25% of their area since 2000 to 2023. And from 2015 to 2016, they lost 17% of their area in 7 to 8 years. So that's giving you this record here. Like these glaciers are losing about over 2% of their area every year at this point. Looking at the larger 2020 to 2023 rate, that's about 1.9 times faster than the fastest rate that occurred in the 20th century, which was from 1900 to about 1945. And it's 3.5 times faster than the average 20th century rate. So that's this rate here. And then if you look at the red dot here, red bar here is showing you the most recent change from 2015 over the last 7 to 8 years, being it's accelerating. In this time frame, Mount Hood has had 2 glaciers that have ceased to flow. One is Palmer, I mentioned, and we'll just look at Gleason next, which is in the Hood River Watershed. And then another 3 glaciers are really getting this declassification, where they go from being to basically becoming like Prince, the glacier formerly known as a glacier. And so that Zigzag and Coleman are going to probably stagnate soon. And then the other one is Langle, which is in the Hood River Watershed. And the reason why we say these 3 is they're losing they lost 40 to 48% of their area in the last 7 to 8 years. So rapid area loss. And the reason for this is, if you look at the regional changes here, this is November through April precipitation, October through May. So kind of defining the winter months here for Oregon. And there's really not much of a trend in the precipitation here. And if anything, recently it's been higher than it was, like, say, earlier on in the 1900s. So you can't say that there's any change in precipitation that would be driving glacier retreat. If anything, it could even been higher more recently. It should have driven a short advance, all other things being equal. And then if you look at June through September or May through October, the summer temperatures, they've warmed for the whole county about 1.7 to 1.8 degrees centigrade, so 3 to 3.2 degrees Fahrenheit since the early 1900s. And so this is what's driving the retreat. It's just gotten hotter, and you know the ice is melting and retreating. It's just that much warmer. So let's look then at the what's happened now in the Hood River Watershed, and this will be Newton-Clark Glacier here, Elliott Glacier, Langell, Coe, Ladd, and then lastly Gleason. And this is looking at the Newton-Clark Glacier, which is in the Clark Drainage Basin and the Newton Creek Drainage Basin. And this is the Clark Drainage Basin here. And the ice that was in this basin is almost completely gone over the last 20 years. And so we could almost start saying that there really isn't an actively flowing glacier in the Clark Drainage Basin. So maybe we should call this just Newton Glacier now, since the Clark component is almost completely gone. Elliott, this is looking at its terminus here in 2003. And you can see it's retreated up here, and there's now bare rock where it used to be ice. Here's looking across Elliott, where these ice falls have thinned down, and you can see a bedrock ridge coming through the ice here that's going to cut it in two, basically leaving stranding this lower component of ice where it can no longer be attached to where the snow survives through the summer at higher elevations and then feeds the glacier flow. This is looking across at Coe and Langell Glacier. In 2003, Langell was already retreating back much higher elevation. So this is already bits of ice that have been cut off, but they're still there in 2003. And by 2023, there's only like a little bit of ice left. And Coe shows this really dramatic thinning and retreat where this ice fall here now is a bedrock ridge. And this is the terminus of the glacier, whereas it used to flow much lower than that. And you get this ridge right here that's now beginning to come in here, cut across there, that's going to cut off this lower component of Coe here in the future. This again is looking up at Coe. Here's where it's flowing over that ice fall, and the terminus is going off to the edge of the picture. And now here's this bedrock ridge that's come through and cut off this component of the ice. And then looking over here at Ladd on the far side, here's this upper area here that's called the accumulation zone, the area that keeps snow year round. And it was flowing down to the lower part of the glacier. And by 2023, off from that. And that occurred since 2015-16. And so in the satellite imagery from 7-8 years ago, these are still connected. So this happened very recently. We can come around and look at Ladd here more directly. Here's that ice flowing down, and again, ice with crevasses is flowing off the edge of the picture. There's ice here now. It's all stagnant and covered with debris. This is actually mapped as not part of the glacier in the 2015-16 survey, but it still is glacier ice there, so it should have been included as formerly flowing ice. And the active ice is up here now at this bedrock, this ice cliff here, this kind of bedrock ridge. And then lastly, this is what happened to Gleason in the last 20 years, or yes, from 2003 to 2023. I mean, it was always a small little glacier. And there's a satellite image. It was first described by the Mazamas in the early 1930s. But it had crevasses in 2003. It was still hanging on, flowing. And then this is what's left of it in 2023. So it's just a smearing of ice left. So here's a summary now of what went through the Hood River watershed. Since 2000, Newton-Clark lost 23% of its area. Its area as of 2015-16, it's lost 18% of that since then, and Clark drainage no longer has any flowing ice in it. Elliott lost the least amount at 12% of its 2000 area, 5% in the last 7 to 8 years. Langell lost the second most, 47% of its area since 2015-16, and it's going towards being a stagnation and then eventually kind of disappearing like Gleason. Coe lost 25% of its area since 2000, 13% of its area in the last 7 to 8 years. Ladd a little less than that, 23% since 2000. We don't have actually a good measurement from 2015-16 of its area because of the improper mapping that occurred because they didn't use field checking, but it has lost part of its accumulation zone. Gleason, 89% of its area since 2015-16, and it's ceased to flow. And then combining the four largest glaciers here, so Newton-Clark, Elliott, Coe, and Ladd, since 2000, they've lost 22% of their area. So these are the four big glaciers in the Hood River watershed. And I'm combining these right now which will become apparent in a second here, because it's been enough time has passed now that we can actually check to see how well model projections that were made in the past have performed. And there was a study published in 2016 by Franz et al. And they were simulating these four main glaciers in the Hood River Watershed, Newton, Clark, Elliott. So here they are, Newton, Clark, Elliott, Coe, and Ladd. And they used as a target the last time there was field mapping in 2004 here. And so they took two climate model simulations, two future projections of climate using one that's a high emission scenario and one that's an intermediate emission scenario. These are the two that the federal government uses in its national climate assessments. And they would then force the glacier model with the temperature and precipitation from the climate model, running and making sure with the parameters that it ran through and matched observations going through the last data point here in 2004, and then let it freely form. And each one of these lines is a simulation varying some different parameters in the model. Red is the high emission scenario and gray is the intermediate emission scenario. And from about 2000 through 2025, they simulate, regardless of the emission scenario, 10 to 30% of the glacier area loss for these four glaciers. And from 2000 through 2023, we find 22% loss. So the model did a really good job of projecting what we can now go back and look and say, oh, yeah, here's what actually did happen. And yeah, it wasn't that bad. And the just for information basis, right now with our current, policies we have, and then all the best wishful thinking of all the global governments saying they're going to cut carbon by this amount over this many years, we're on this intermediate emission pathway right now that will result in, about 2.7 degrees C of global warming by the end of the century. That's our current pathway we're on. And so that's the gray lines here, which show in general some ice remaining on Mount Hood by the end of the century. Still a lot less, but it's not going to completely deglaciate. And the model did a decent job so far. When we can go back and look at it now. So I want to then take a little step back here and look about how unprecedented is this change that we're seeing in the Hood River on Mount Hood. And so I was able to, we have photographs going back to 1901 of glaciers on Mount Hood, the classic one of Elliott Glacier and that boulder taken in 1901. And we can then look further back at the climate here. What I'm showing in this graph here is the red line here is atmospheric CO2. I should update this because we're actually up at 425 ppm now. This is from last year when we hit about 2 years ago. We were 419. We were 421 last year. Now we're 2 years ago. Now we're at 425. And then down here is the ice core showing that, up until the 1800s, it was relatively constant around 280 to 290 parts per million, and then it took off. And below then, the dark blue is showing you a tree ring reconstruction of summer temperature for Oregon, Washington, and southern British Columbia. And then the light blue behind it is temperature data from the exact same region. This is from the Hadley Center, which Dick showed one of their records for the global temperature in his slides there. So this is the English temperature product. Anyways, what you can see is prior to this takeoff and warming of summers, the Pacific Northwest had a relatively constant, stable climate going back over 1,000 years. Not much of a trend in there. There's some warmer areas and cooler periods, but not anything going really crazy. Now we can look at Elliott Glacier has the most research conducted on it. And there was a study back in 1948 published in the Mazama Bulletin, so the mountaineering group in Portland, that pushed back that there's old rain they found that they had a tree on it that growing in the 1500s. So they found moraines for Elliott Glacier around to an extent that go back prior to this. So the Elliott Glacier was around its maximum late 1900 extent for at least, the prior 700 years, 600 years earlier. So how far does this history go back? And this is going to then show you the figure here. And this is from that paper. This is their air photo from 1948. And then this is their mapping of it. And this is a spot that's 1300. They identified a bunch of other moraines on here and used volcanic ashes to identify their ages. And then we looked at these two moraines outboard here that they placed as being older than 1500 and 1650. And we went out and a colleague of mine at Imperial College London, we collected samples of boulders from these moraines to measure how long they've been exposed to cosmic radiation from outer space. And in volcanic rocks, when these things hit olivine and pyroxene, they will produce an isotope called helium-3 in the crystal lattice. And that then, as it accumulates, it then tells you how old the rock is, just kind of like a sunburn would tell you how long you've been out in the sun, or a common thing that used to be used before this was how big are the lichens on the boulders. This is looking at standing on the moraine right here on the historical moraine. And then it's really hard to photograph these things. These run off right here. This green going down here is the beginning of these older moraines when they come up and meet the 1900, 1901 moraine here. And this is what the boulders on there look like. So you're taking the surface samples of these, and then we collected 11 samples per moraine. And here's what you get. And it really was astounding how old these moraines are. The outer one is over 5,400 years ago, plus or minus 200 years. And then the inner one is 3,000 years ago, plus or minus 200 years. And so this means basically that Elliott Glacier has existed. Climate has been able to sustain Elliott Glacier around its 1900 extent. So the historic maximum extent over 5,000 years. Just for context, 5,400 years ago is when cuneiform writing is the oldest evidence of cuneiform writing in Sumer. So Elliott Glacier was around its 1900 extent. As long as we've been able to ever write down that Elliott Glacier is around its 1900 extent in a clay tablet. So this is like shows you like basically how far we are changing the hydroclimate of this region that has existed for millennia. So just kind of to summarize this up here then, the summer warming for the region, not like a point location like Nick was showing, about 1.7 to 1.8 C, 3 degrees Fahrenheit, is now driving glaciers on Mount Hood losing over 2% of their area per year. In the Hood River Watershed, one glacier has ceased to flow and another is nearing that status. Now, these are the smaller ones. The four largest ones, though, lost 22% of their area in the 21st century already. And basically, our greenhouse gas emissions from burning fossil fuels have reversed 5,000 years of glacier presence in Hood River Watershed, sending it to conditions that have not been seen for many, 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 many millennia. So that's, I'm happy to take any questions.
Thank you, Anders. Do we have questions in the audience?
I have a question for your prehistoric temperature change graph. How are they measuring? How do they have data from 1,000 year to 1,000?
Back here, this one?
No, keep going. That one. How do we have? That one.
Next.
One?
Tree rings? Is that how we have the temperature from 9,900?
These are tree ring growth records, and the idea that they're tree ring growth records is they're not true. They don't use tree ring width anymore. They look at the density of the wood in a given year, and so it's a density record. But they're still measuring tree rings, but it's like how much basically cellular mass is in a weight.
Yep.
So thanks very much for this really interesting data. Given the rate of loss of glacier water, can you estimate how long the agricultural resource of the Hood River Valley can continue to have water for fruit trees?
That's
So one of the things we'll do next, at our next talk is look at the hydrologic forecast. Based on the informed by glacial reckoning. So do your best, but you don't have to completely.
it's a good question, and the Font study was actually focused precisely on predicting that the changes in the hydrograph for these points downstream. And I know the Hood River Watershed Group has been incorporating this model into their projections. The peak melt is already passed. So like as a basin deglaciates, initially you get more meltwater as the glaciers start to retreat, and then you hit what's called peak water, and then you're on the decaying end. And a study Ann Nolan did on Elliott Glacier, she published in 2010, argued that peak meltwater had already passed by that point. So we're on the declining side of how much water is going to be coming from these glaciers, whereas this actually exact same model was used in a study for British Columbia, finding that the glaciers up there, peak water is coming there. So the hydroelectric power from British Columbia Hydroelectric is going to increase going forward as the glaciers melt. And then it decline later on in this century. It will decline. The dark gray line here is the best estimate of all those runs. And so like if you kind of look across here, 75, you're going to lose another 50, relative to 2000, you're going to lose 50% of the glacier area they're estimating. So there will still be a component of glacial meltwater in this region. The question just becomes like, how far down, as you move towards the lower streams here, how important is the glacial meltwater at that level to keeping the streams going versus the higher upper reaches? And I think Ann Nolan suggested the upper parts in the late summer, the flow is about 70% from glacial meltwater, and but much further down into the drainage basin, it's much lower. So upper reaches, it could get quite low, but Mount Hood will probably be, if things go as we plan right now, I would bet that Mount Hood will still have glaciers in the Hood River watershed at the end of this century, as long as we don't go and start burning more fossil fuels than we are. And the thing is, we can always do better and bring this gray line up if we stop burning fossil fuels. So that was a kind of a non-answer to swing around it, but as Cindy said, I think there'll be more information on this in a couple of weeks.
Yeah, this is Dick Iverson. So I have one easy question and one hard. The easy one is, did you work with my brother beneath the glacier in Norway in the tunnel?
No, I was telling Cindy about it. I applied to do a PhD with him. So I went stayed in 2002. I was in Ames, Iowa, visiting him, and then I did part of my PhD work was working with triaxial shear devices on subglacial sediment deformation. So I worked with engineers in Arizona doing similar work to his ring shear work. So we met and talked at many a meeting, but I did not end up going to Ames. Yeah, but I was telling her about his work underneath the glacier in Norway and the cool stuff he did there.
So the hard question is, have you tried to estimate volume as well as aerial loss for the glaciers?
Yeah, that's a good question, and we have not. There's I know like Andrew Fountain does this when he does his mapping, and he's the one who produced the 2004 ice margins and the 2015-16 margins we're using here. And it's the scaling functions that they use for that almost always are based, at least the training, I mean, I've done this for ice sheets. They're assuming that the glacier is in equilibrium with climate. You have the area of the glaciers here, and the glacier area versus its volume follows a power law, and so you can they've lined up very nicely. And most of the relationship built on data from the 1950s and 60s when they're first developing this. And that's a period where it was colder and wetter in the Pacific Northwest. The glaciers were expanded and happy and inflated, I guess you would say. And if you look at just these photos, see if I can get one here. There's like this area of change between here and here. This is like it's already deglaciating. So the area would be adding more ice into this area here than really is there. So we've not done that extra step. I could easily do it. I just haven't done it because I feel it's the relationship reflects glaciers and healthy glaciers in equilibrium with their climate versus ones that are in dysregulation and disequilibrium. So.
Thanks.
I also have two questions, and one is you talk a lot about, or you pointed out in these photos where the glaciers were split by like a ridge as they started to retreat. I'm just curious, like, does that increase the pace of their disappearance like below that ridge, or is that just something you just kind of pointed out?
It will. It will increase the rate because let's see here if I can get a good photo. Yeah. So this you have Co here flowing down here and it's going off the edge of the screen. And when this photo was taken, it had just had some fresh snow on it. These are all from late September, and it happened to recently snow when Steve Boyer went out there in 2003. So it's not nearly as white as it would have been if you would have been here like a week before then, that day period. But what happens is it's just like if you build a dam or divert water away from a lake that's down lower, that lake will cease to get that water and it'll shrink in size as it evaporates. It has no longer replenishment. And the same is true here with the glacier ridge coming through. The ice below this bedrock ridge here over this ice fall, it melts every year. And part of that, if the glacier was in equilibrium with climate, all that melt down here would be replenished in the year by the flowing of ice from up above to back to here to replace it. And when a glacier is retreating, it what happens is it melts more than the flow of ice from higher elevations can replenish it in that year. And over time, that then makes it retreat because it's losing more than it can be replaced. Because the glacier is always flowing forward, and the retreat is rather the melt back faster than rate of flow down to replace it. And then what happens with a ridge is you cut off that supply altogether. And then the ice flow here it can still flow, but it eventually it's not getting replaced at all. And this would be a good example here on Zigzag, where the ice is flowing down all the way along here. And this is thinned down now, where you still have ice in these areas, and they are no longer getting any replenishment from higher elevations. So it speeds it up. Yeah. It's
Yeah,
not
that's helpful, and that kind of leads into the next question. So I definitely didn't see it in the forecast for the next 100 years, but like, are there ways to build back glaciers? What does that take?
Well, there is a hope here. One is that the glacier, you don't follow the high emissions scenario, which could have had some of those simulations had no ice remaining on Mount Hood by the end of the century. Some is left. These glaciers, the Pacific Northwest really wants to have glaciers if it's just cold enough, because we get so much snow that the area it's really primed to grow ice, and we just have to keep it cold enough for that to occur. And so, the most straightforward thing to do is get off of fossil fuels. Allow natural carbon sinks to suck CO2 down, and the climate will cool. And my great grandkids might get to see glaciers regrowing. The other way to do it, to try to preserve things, is people question, whether I hear from people like not liking what Timberline Lodge does to move snow to higher elevations. and they spray magnesium chloride on it in the summers to change its melting temperature to keep the snow around. But that also is simulating a fake glacier. They're artificially replenishing snow in this area here that, by September it's gone and they don't have the ski camps there anymore. They don't run year round anymore. But through August, they're keeping snow in that drainage basin that would not be there otherwise. And so those, the area below it would not be getting any meltwater if it wasn't, except for the actions of Timberline Lodge. So you can argue about, the manipulation of the hydrologic cycle in that little area there, but they are sustaining snow in ways that would otherwise, they're basically making a fake glacier for most of the year. You can, like in Europe, they're doing things with mats to try to slow melting. The conundrum we have with in the Pacific North and Oregon is that our glaciers, except for a bit of White River Glacier, are all in wilderness areas. And so, you can't get a permit to go put a mat on a glacier that way. You can farm snow, or you can try to slow the melting by putting mats on it, blankets. And the best thing to do would be is to try to cool the climate, I think. That's a long.
Thank you, Anders. Any last questions? You can shout it out. Bernie, just say it.
So Dick Iverson had a plot on the different greenhouse gases. Dick Iverson had a plot on the different greenhouse gases. If we succeed in reducing carbon dioxide emissions, is that going to be enough to halt the growth in methane emissions from things like melting Siberian permafrost? So should we be paying more attention to sources of increasing methane emissions?
Dick,
That's me or Dick?
Dick saying you,
Me?
You. Anders.
Okay. That's a good question. Methane and CO2 are two different. They behave differently. The CO2 is, if you wanted to cool climate rapidly, we should, if we ended anthropogenic methane emissions like tomorrow, in 10 years, all other things being equal, we could cool the globe about 0.2 to 0.3 degrees centigrade. Because methane stays in the atmosphere for 12 years at around on average, and then it breaks down into CO2. But it's much lower concentration, so you barely notice it in the CO2 record after 12 years. But in that 12 years, it does a lot more warming than a per part per billion, as relative to a part per billion for a carbon dioxide molecule. So you shut off the methane, you can quickly cool the climate because it disappears. The issue there is that the long-term warming, looking at the century glacier time scale, human lifetime time scale, it's really being driven by CO2. And that takes much longer to draw down. And that's what sets, I guess you can think about it like, the long-term trend of warming is CO2, and then not all the wiggles, but like the methane is a amplifying effect. And if we want to stop the methane being released from permafrost, the main thing we need to do is cool the climate so we can stop that kind of melting. And the ways of mitigating the two, so like ending methane versus ending CO2, are quite different. They're two different things. Like 1/3 of methane emissions come from fossil fuels. So methane is natural gas. And so when we oil wells and natural gas wells leak methane like mad, and 1/3 of the emissions of methane just come from the fossil fuels that also supply the CO2. Another third is from livestock, and that quickly becomes a different thing where you're talking about animals that then 10,000 years versus something we covered 150 or started to use at an industrial scale 150 years ago. So it's you can point to something that changed in 1800s that we'll probably have, whereas more cows on the planet has increased methane emissions, but we've had cows for 2,000 years. The current problem isn't being driven by cows. It's adding to it, but it's not the main source. And so I think the way to address this is to look at to find a long-term solution is addressing CO2. But if you wanted to cool climate quickly, you're right. You would reduce methane emissions for immediate effect.
Thank you, Anders. I think we'll wrap it up there. Let's give a round of applause.